Heating and cooling curves are these graphs that show the relationship between temperature as something is heated or cooled, so over time. Um, a heating curve shows how the temperature of a substance changes as energy is added. A cooling curve shows the temperature, but as energy is removed. So they're really the exact same thing, just opposite, flipped of each other. So let's take a kind of closer look at this heating and cooling curve, and we can see what's going on here. These are really useful when you're trying to figure out kind of like what's happening to a substance at different temperatures. It can help you identify boiling points and melting points. It's similar to a phase change diagram in some ways, except for that it's specific to one pressure. So pressure is always constant. Let me add that in here real quick. Pressure is constant. So you actually could make a heating and cooling curve for different pressures, and it would be completely different graphs. Okay, so excuse me. This heating curve shows us, this is very generic for just any generic substance. It starts off in a corner here, and you can see that this is the solid phase. So in this case, as more and more heat is absorbed and more heat is added over time, the solid starts to heat up. And this is the point where it's melting. So the reason that we kind of know this is because thinking back to, this is all related to specific heat and heat of fusion and heat of vaporization. If you're within a certain phase of matter, as you add heat, the temperature rises. But at a certain point, if a solid is melting into a liquid, the temperature stops changing, but the phase changes. So that's why here you'll notice it's a flat line, because the temperature isn't changing, just the phase. But as soon as all of the solid has been melted into a liquid, now it's all in one phase, and any extra energy is just going to raise the temperature. So that's kind of represented by this line. And then you hit the boiling point. So this line here is the boiling or vaporization or condensation point, where the water or whatever this is, the substance, is now being converted to a liquid to gas. And again, at this point, the temperature isn't changing, only the phase. And you'll notice kind of here that it seems to take a lot more energy, like it takes a lot more time, so probably therefore more energy to completely boil a liquid into a gas versus to convert a solid to a liquid. The final step is now that once all the liquid has been converted to a gas, the gas can heat up. So those are kind of the phases represented by this. The slopes of these lines will give us some information and some idea as to the specific heat. So like how much energy does it take to change the heat? It looks like this slope is a little bit more shallow. This is a bit steeper maybe. So maybe that means that the specific heat of the liquid is a little bit lower. It takes less energy to change the temperature of this liquid than solid. It's hard to tell here, but maybe that's what's happening. Anyway, what's good to know about these is to be able to look at this and identify what's happening. And understand what each of these different lines means. So knowing that this part probably means a solid, that's the melting point, there's a liquid, there's a vaporization or boiling point, and then finally the gas. And you can use this to help solve problems like the ones that we're about to do. A cooling curve here is the exact opposite. So you're starting at a gas and it's cooling down into a liquid. Once it's all completely liquid, the liquid cools off. Once it's all completely a liquid, or like once the liquid is cooled off and you've hit the melting point, it turns into a solid, and then the solid can start to cool off. Okay, so let's take a look at one of these problems. I've got two of them. Excellent. Okay, so how much energy must be removed to make 150 grams of ice at negative 15 degrees Celsius from water that is at 25 degrees Celsius? So let's do this. I'm going to draw a really quick little cooling curve because it looks like, oh no, heating curve, cooling. Yes, cooling curve, because we are starting with water at 25 degrees Celsius and we are going to ice at -15. So that's kind of where that's our start. And that's the finish. That's what we're looking for. And we've got a whole bunch of information here that I think is going to be important. So let's put this all together. So if I make a real quick little cooling curve here for water, we've got temperature and we've got heat removed. That's in joules. This is in degrees Celsius. Okay. We know that water starts off as a gas here. It's going to cool off at the boiling point is 100 degrees Celsius. So that line is 100 degrees Celsius. And this line is probably 0. It's going to, so this is a gas. We've got a gas that's turning into a liquid. We now have a liquid that's cooling off until it hits 0, which it then converts into a solid. That's the melting point, and then it cools off further. Okay. So the 100, oh, sorry, you guys can really see it. The 100 and the 0 are again the boiling and the melting point. So what this problem is asking us is we are starting with water that's at 25 degrees Celsius. So we're probably starting about here. And we want to cool this water all the way down to ice that's at like -25 degrees Celsius. So what we have to think about here is, first of all, there's 3 steps to this problem. Because if we kind of follow along the curve, we can see that there's 3 separate lines that we need to contend with. The first one is cooling the liquid down from 25 degrees Celsius to its melting point of 0. So this is the cooling water stage, cooling the liquid stage. Then we need to freeze it. This is the freezing stage. And then finally is cooling the solid. So the funky part about this is kind of figuring out how do we solve for each of these parts now that we've kind of broken it down. And what's going to happen is as the liquid cools off, it's going to release heat. And this is one where we're going to want to use specific heat because we're dealing with a temperature change. The freezing, we're going to be using the heat of fusion, no temperature change, but heat of fusion. And then finally cooling the solid, we're going to go right back and use the specific heat formula again. Okay. So 3 different formulas, 3 different problems. So let's kind of solve for each one. If we start with the cooling of the liquid, so cooling liquid water, it looks like we have 150 grams of ice, Q equals MC delta T, and this is the C of liquid water. We've got 150 grams of ice. Now we need the specific heat of liquid water. So there's 2 different specific heats here. There's one for liquid water and one for solid water. We want the liquid one. 4.2 joules per gram degrees Celsius. And we need to multiply that by the temperature change. Our temperature is starting, our initial temperature is 25 degrees Celsius and our final is 0. So that's 0 minus 25. Sorry, I'm running out of space here, y'all. It's going to be an issue with this problem, but we'll do our best. So 150 times 4.2 times, that's going to be -25. Oops, not. All right, so we have, negative 15,750 joules. It's negative because it's losing heat. It's releasing heat out into the world, or it's being absorbed, removed. Okay, so this is the amount of energy to get water to 0 degrees Celsius. It's not a liquid, it's not a solid yet, it's just getting to that. Now we need to actually freeze the water. So freezing the liquid. That's next step. That's going to be our Q equals M heat of fusion. So we have our mass of water, it's 150 grams. And the heat of fusion is right here, 334 joules per gram. So our answer is going to be 150 times 334. That's 50,100 joules. And that's also going to be a negative number. Didn't really say there, but it's, because you're losing heat. Okay, final stage. So again, we've so far we've followed this part of the curve. We just did this part, and now we need this last step. We need the cooling solid. Cooling the solid. Okay. The solid, this is going to be Q equals MC delta T. And in this case, our mass is definitely still 150 grams. We need the specific heat of solid water, which is 2.1 joules per gram. And the temperature change, sorry, bloop, bloop. We'll go just kind of do a little dividing line there. Our final temperature is going to be, what is it, -15, but we were starting at 0. So that's just going to be -15. So we're going to take 150 times 2.1 times -15 because it's losing some heat. And that's -4,725 joules. Okay, so this is the total amount of energy from each of these individual steps, or those are the amounts of energy from the 3 steps. Now we just need to add them all together. So if we take all 3 of those numbers and we add them all together, plus -5 and plus -15,750. Yep. Oops. Okay, it looks like our final answer is -36,225 joules. That's how much energy that needs to be removed from water in order to freeze it, which is pretty much what happens when you make ice. Your freezer is actually probably -4 degrees Celsius. It's probably not -15, but if you had a really good freezer set to the lowest number, maybe. That's how much energy you have to remove in order to make just room temperature water, which is like 25 degrees Celsius, into ice. And 150 grams of water would probably be a couple ice cubes. So that's a fair amount of energy right there. So again, it's these 3 problems, these 3 different steps. Okay, we just add those 3 numbers together and we get our final number. If you put a positive number instead of a negative, that's fine, as long as you understand the concept, it's cool. You can also obviously convert this to kilojoules if you want, because that can be kind of fun, because kilojoules are a little bit more manageable. Okay, let's try another one. We'll see if this makes sense. Ooh, I've got a little bit more space for that one, so that's good. Okay, so how much energy is needed to vaporize 35 grams of ethanol from 25 degrees Celsius to 95 degrees Celsius? The boiling point of ethanol is 78 degrees Celsius. We've got the specific heat of liquid ethanol and the specific heat of ethanol vapor. And we're going to need also the heat of vaporization. I just realized I didn't give that to you. The heat of vaporization for ethanol is a number. Let's see what it is. I'll check the internet real quick. Ethanol. Okay. Okay. Hold on. I'm gonna have to look it up. 1 second. All right. I had to look it up, then I had to do a quick conversion. But anyways, I got the number here. It's 836.99 joules per gram. Okay. So let's do this looks like a heating curve. So let's just draw out a quick heating curve so we can keep track of what's going on here. This is going to be heat absorbed. It's in joules. And we've got temperature, which is in degrees Celsius. Pen is dying. I'll have to get a new pen pretty soon here. Okay, so we're going to start here. We've got this solid and we've got a liquid, or converting into a liquid. I don't really know what the melting point of ethanol, it wasn't really given to us, but it doesn't really matter. I don't think. We do here have, this is the solid to liquid, this is liquid, this is the liquid to gas, and that's the gas. This temperature would appear to be 78 degrees. Okay, so that's the melting point or the vaporization point. And it looks like we are starting at 25 degrees Celsius, which I'm going to assume that's a liquid. You guys actually probably have experienced ethanol. Ethanol is alcohol. So it's going to be somewhere in the liquid stage. We need to bring it up to 78 degrees, boil it, and then bring it further up to 95 degrees. So something like that. So once again, we've got 3 steps. So let's do it. So we need to heat the liquid. That's one step. We need to boil the liquid. So phase change. And so we'll start with those, and then we need to heat the gas, but we'll see. I want to see how it fits, if I can fit all this information here, how we do that. Anyway, heating liquid is Q equals MC delta T. We need our mass, which is 35 grams. We need our specific heat of liquid ethanol, which is 2.57 joules per gram degree Celsius. We'll do that. We'll give ourselves a little bit more room here. Times our temperature change. We are starting off at 25 degrees Celsius, but we need our final has to be 78 degrees Celsius because that's how much we need to heat it up to get it to the point where it will start to boil. So that's this first step here. Sorry, this first step right here corresponds to that. So let's just go ahead and give our answer here. So we'll do that. We'll do boil liquid. Setting this up. Gosh, my pen. Do I have a spare pen somewhere? I don't know, do I? Sometimes I keep one handy and sometimes I don't. I do. Oh dear. Sorry about that. Sorry about the bell there. So loud and obnoxious. Yeah, that's pretty much dead. We'll get rid of that one. Okay, so we're going to need to boil the liquid after this, and then finally we're going to need to heat the gas. Okay, so we've got our formula all here. Let's plug in all these numbers. Looks like we've got 35 degrees times, what was that, 2.57? Oh my gosh. Wow, my handwriting is pretty horrendous, isn't it? I'm trying here. Times 78 minus 25, which I could do in my head, that's 53. Okay, so we get our answer here of 4767.35 joules. So that's much energy we're going to have to add just to heat the ethanol up to its boiling point. The next step is we need to boil the liquid. So we know with boiling liquid, we're using the heat of vaporization. So that's going to be Q equals M and the heat of vaporization. So that's 35 grams times the heat of vaporization. I just had to calculate that was 836.99 joules per gram. So we just need to multiply those two numbers together. And this again represents actually like the phase change, no temperature change, just a phase change. Sorry, you guys can't see that. I had it way off the screen there. So that looks like 29,294.65 joules. And our last step is heating up the gas. So this is that last step. If we're heating something, that's specific heat, 35 grams. The specific heat of, now we're at ethanol vapor. So that's the 2.818. Very similar numbers, not that far off from each other. That doesn't really surprise me. There's not a lot of intermolecular forces. Oh, and I forgot, sorry, temperature change. We are starting at 78 degrees Celsius, but we need to bring it all the way up to 95 degrees Celsius. So that's that. So 35 times 2.18 times 95 minus 78, which I probably could do in my head, but I'm not going to. I don't have to. What calculators are for. It looks like, oh, that's not a lot. Oh, yeah, because we're not really raising the temperature. That must be why. Okay, so we have these three numbers. All we got to do now, add them together. 29, oh gosh, okay, 29,294.65 plus 4767.35. 47. Yeah, that should be good. Okay, and it looks like our total answer is 35,359.1 joules. Or 35.36 kilojoules. Okay. So that's how much energy it takes to boil some ethanol. That's the kind of problems that it's good to know how to do. All right. That is the trickiest thing that I could probably give you. Technically, you could kind of solve it for the whole heating curve, but I'm not going to make you do that. Taking a look at your packet, I've got page 16 and 17, and I believe 18 and 19 are all related to this topic. And 18 and 19, when you actually take a look at this, mostly this is asking more about the concepts. So you don't even really have to know, it's less about the calculation, it's more about like what this heating curve actually means. So you guys can take a look at that, and I will definitely have an answer key available. Let's stop there, and we will continue to learn a lot more about phase changes, but specifically gases in our next unit on gas laws. So thanks, y'all.